and today we are covering acids and bases. You can find some great resources right here on OpenStax acid-base chapter. This PowerPoint is available to download in my Canvas course. Feel free to click on the link and get some good reading in. Alrighty, so on to the first slide and the second slide, properties of acids and bases. It's very simply, acids taste sour. We find it apples, vinegar, lemon, especially that vinegar. If you like to eat it with some of your foods, you notice that the vinegar is quite sour. That is an acid. It also makes your fingers feel, here's a new word for you, frictiony. You know how you rub your fingers together after you've peeled an orange? That is because of the citric acid in the orange. It makes it feel what I call frictiony. Properties of bases. Bases taste sour. This would be some of your cheeses, especially your Gorgonzola, feta cheese. They are very high in a base factor. They also feel very slippery, much like dish soap or some of your laundry detergents feel slippery. That's because they are bases. Acids and bases react with each other to form a salt and water solution, and this is called a neutralization reactions. I like to say that an acid assaults a base to create salt and water. And here's an example. We have a base and we have an acid to produce water and salt right there. Types of acids. We have several different types. We're only going to focus on some of them, but the most common acids are called binary acids. This would be your hydrogen chloride, your hydrogen fluoride, and oddly enough, water is a binary acid. Binary in the sense that it's made up of only two different elements. And that means if we have a binary, we must have something more. Those would fall under the oxyacids. Oxy for oxygen. As we can see, all of these have oxygen within them. They don't all have to have hydrogen in the beginning, but for this example, they do. And so this one would be called nitric acid, nitrite, or nitrous acid. And then sulfuric acid. That's how we would name those. We'll cover nomenclature, the system of naming in a different chapter. And just so you know, here's some more. These are not on the test. These are called organic acids. Here is one. You also have a very common one for the vast majority of students. That would be called carbonic acid. What happens when we put carbon dioxide in water, and we get some really good stuff out of that. Okay, three different definitions that are accepted. We are only going to follow or focus on two definitions. Lewis acids we will not cover. They will not be on my test. We will focus on Arrhenius and Bronsted-Lowry definitions of acids today. Okay, the Arrhenius definition. The acid is a substance that disassociates in water to form hydrogen ions. Well, what the heck does disassociation mean, or disassociate? Dis meaning opposite. The opposite of associate would be to break apart. Okay? A base is a substitute that disassociates hydroxide ions or OH ions. Once again, disassociate, it breaks apart. Okay, Bronsted-Lowry definitions. This is what we will focus on for most of our equations. An acid is a substance that can donate a hydrogen ion. And then a base, a substance that can accept hydrogen ions. Both of these are present when reactions occur when a compound is dissolved in water, and that's why we we'll really focus on Bronsted-Lowry definitions. It's a simple definition that covers the majority of compounds that are considered to be acids or bases. Okay, the definition, like I said, it does broaden the idea of what an acid or a base is. Examples. If you look at this example, which of these is losing the hydrogen ion? If it loses the hydrogen ion, that means it is the acid. If it's going to gain the hydrogen ion, that means that it will be the base. All right. And since the hydrogen chloride gave away the hydrogen to become a chlorine atom, that is why it is the acid. And the opposite must be the base. Now for the conjugate acid and base, that means that this will be the opposites, or going the opposite direction in the reaction. Okay? A pair of compounds that differ by only one hydrogen ion. When an acid loses the hydrogen ion, what remains becomes the conjugate base. It may seem a little confusing. I'll make it simpler on one of the next slides. When a base gains a hydrogen ion, what forms is the conjugate acid. And why do we have the definition of a hydrogen donator? So that the original base has an extra hydrogen and becomes the donator. So here we have the same reaction again. We already identified our acids and bases. And now let's just think of this doing something a little bit different. Let's flip this arrow as if it was going to the left. And which of these is losing the hydrogen ion, which is gaining the hydrogen ion? If you notice, this H3O, or what's called the hydronium ion, it is actually going to lose the hydrogen. Therefore, by definition, it must be an acid, and the chlorine ion will gain the hydrogen. Therefore, it must be a base. So this is called the conjugate base, and therefore the hydronium ion would be called the conjugate acid. Right? And so if you just think of reversing the arrow and going with the same Bronsted-Lowry definitions, and it's a little bit easier to decide which is going to be the conjugate acid and conjugate base. Okay? And so we've got another equation here. Try to identify, hit pause on the screen and try to identify which is going to be the conjugate acid and which is going to be the conjugate base with this example right here. Okay? I'll see you on the next slide. All right, the substance acid or base indicators. These help to identify acids and bases. They turn colors based upon that. Now, if you download the PowerPoint, you can actually click on these links. These are YouTube links. They're not mine, therefore I'm not going to show them on my video. Other teachers and presenters have done these, and I think that they're high quality enough that I included them on my slides. So please feel free to click on these and learn more about those. But acid-base indicators are substances that will change colors based upon the type of solution they're in, if they're in an acid solution or a base solution. And these can also change based upon the intensity of the acid or the intensity of the base. They will change different colors. There are many types of acid-base indicators, and so we can find many different wonderful things to use them for, to turn many different colors that we want to use, as well as to find the intensity. Okay. The most common that is used is litmus paper. This is what we would use within the classroom, as well as phenolphthalein. This is clear in an acid, but it turns pink in a base, and so it's fun to play with. All right, so how in the world does an acid form? An acid utilizes the hydrogen bonds, or it takes advantage of a situation with the hydrogen bonds. Here we see two different water molecules. As we've learned previously with the polarity of a water molecule, the water molecule forms a dipole. Once again, di meaning two, and pole meaning a electromagnetic pole. So we're going to have this side is going to be a partially positive, this side is going to be partially negative. We have more electrons here, and because the hydrogen proton, or the proton in the hydrogen atom, this is going to be more positive. If these water molecules get too close together, or maybe they bump together in just the right position, one of these water molecules is going to snag the other's hydrogen atom. And so what we find here is the hydronium ion as it is snagged it. It might only snag it for a fraction of a second, leaving them oddly different. Here the hydronium ion, here the hydroxide ion. This happens in just pure water. This happens 1 in every 10 million pairs of water molecules. And so we see this if we were to go to Las Vegas and figure out how to bet or buy a lottery ticket. This happens 1 in every 10 million, and therefore this is the scientific notation of what we have. 1 times 10 to the negative 7. Now that becomes very important as we go to the pH scale. The pH scale is used to determine the acidity or the basicity of a solution, or the alkalinity is how some will say basicity. Based on the ionization of water, pure water, the concentration of the hydrogen and the hydrogen ions and the hydroxide ions will always be equal as long as it's pure water. Here we go with that number again. Okay, here's our concentration. 1 in every 10 million pairs will become that number, 1 times 10 to the negative 7. Normal range for a pH scale is 0 to 14. We can go outside of it, but it's not normal. And so here we see our pH on the bottom. pH of 7 is right in the middle. Therefore, 0 to 14 is the normal. We also see this pOH. We're going to talk about that a little bit later. But we have our pH scale of 0 to 14. Right in the middle is 7. Therefore, we see that 7 again, times 10 to the negative 7. Okay, and here we go. Acid solutions have a value or a molarity that is less than 1 times, or have hydrogen ions that happen more than 1 times 10 to the negative 7 values. Base solution, we see the OH concentration is greater than 1 in every 10 million. And so if we use this little math equation right here, go ahead and hit pause on the video, write this equation down because we will be putting it into a calculator soon. Okay, and now you're back. As we look at this, the pH scale is a logarithmic scale, just like the earthquakes that we've been going through lately. It is a logarithmic scale. The further away that we get from the negative 7, that means we are 10 times the concentration. So a pH of 8, while it is only 1 digit away from a negative 7, it is 10 times. Okay, and so here's another video for you to watch on how to use some of these equations. Feel free to click on it when you download the PowerPoint. But these equations, you want to write down each of these. We will be using these two on a worksheet today. And notice that when I have these two together, we form a value of 10 to the negative 14. Therefore, if we combine our pH and our pOH, we always get a value of 14. It doesn't matter if the pH is a negative value or the pOH is a negative value. We will always get back to 14 as we look at the relationship of them. If a pH is 6, then pOH must be 8 so that we can get back to 14. Okay, here's another equation. The molarity of the first sample times the volume of the second sample equals the molarity of the second sample times the volume of the second sample. We might use this in this odd year with COVID-19, but more than likely this is going to be used on a different year.